Math 2414, other convergence test video 7, the alternating series test. For the students in my current class, this is the beginning of section 8.4. Let's start by first defining what we mean by an alternating series. If I can get untongue-tied, hold on a second. Come back here. Hold on a second. We've seen alternating series. We just didn't formally define them. But an alternating series is a series of the form, looks like this, or it looks like that. And if you look closely, the only difference between the two is whether the exponent matches the index or is off by 1. By the way, it doesn't have to, in the second one, it doesn't have to be n minus 1. It can be n plus 1, be n plus 3, or n plus or minus any odd number. And this doesn't just have to be n, it can be n plus or minus any even number. So it could be like n minus 2 or n plus 4. But usually it'll be n plus 1, or n minus 1. And the reason it only needs to be one of those two is we know that negative 1 to a power oscillates between 1 and negative 1. So we just need to make sure that if we want it to start positive, then our first power of negative 1 needs to be even. And if we want it to start negative, then our first power of negative 1 needs to be odd. In the first one, because this starts at 1, which is odd, then the first term in this series would be negative. But in the second one, since n equals 1, but n minus 1 is 0, which is even, then the first term in that series would start out positive. But that's the only difference between having negative 1 to an n power or negative 1 to an n minus 1 or an n plus 1 power, is whether the alternating series starts positive or negative. But to truly be alternating, the alternator needs to be the only thing that's changing signs, meaning that whatever follows it can't change signs. So the easiest way to define it is just to say that it's never negative, meaning that it's greater than or equal to 0 for every n greater than or equal to 1, or wherever our series begins. That's the formal definition of an alternating series. It's got an alternator followed by something that doesn't change signs. So we just define it to be positive. What's the alternating series test? Well, the alternating series test requires actually 3 criteria. Number 1, your sequence is eventually decreasing. And again, when I write this, I mean the individual terms in the alternating series without the alternator. But the sequence without the alternator is eventually decreasing. All the terms are non-negative. That's kind of implied from the definition of alternating series. And the limit as n goes to infinity of the term without the alternator goes to 0. But if all 3 of those things happen, then the conclusion that you draw is that the alternating series, converges. That would be bad to start off with a wrong conclusion. Horrible. Fix that. Let me say it again. Alternating series test. You have an alternating series where the terms without the alternator are positive. That's this piece over here. Where the terms without the alternator are positive, the terms without the alternator are eventually decreasing, and the limit of the terms without the alternator goes to 0. So basically, you ignore the alternator once you realize it's an alternating series. But if without the alternator, the terms are positive, decreasing, and approaching 0, then the alternating series converges. So we got 3 criteria to check. And let's do that. Got 3 examples lined up. Example 1. Determine if the following series converges or diverges. We have the sum, n equals 1 to infinity, of negative 1 to the n plus 1 over n. This series has a name. If I write out some terms, you'll see why it's called that. Let's just write out a few terms. If n equals 1, then the numerator is negative 1 squared, which is 1, and the denominator is 1. If n equals 2, then the numerator is negative 1 to the 3rd power, which is negative 1 over 2. If n equals 3, getting ahead of myself, if n equals 3, then the numerator is negative 1 to the 4th power, which is positive 1 over 3. And then it would be minus 1 over 4, plus 1 over 5, minus 1 over 6, etc., etc. This is almost the harmonic series, except it's alternating. So appropriately enough, guess what this thing is called? This thing is called the alternating harmonic series. Big surprise, real clever name there, but it describes it perfectly. It's alternating, and without the alternator, it's harmonic. All right, so if we're going to use the alternating series test, First thing we have to do is identify what the term is without the alternator, and that's pretty easy. Our term without the alternator is 1 over n. Remove the alternator, which leaves a 1 in the numerator. And we have to check that 3 things happen. Number 1, this is always positive. It is. Remember, we took off the alternator. And more specifically, non-negative, and no, those are not synonyms. Positive means greater than 0. Non-negative means not negative, which means greater than or equal to 0. But this is always positive. It's clearly decreasing. Not cleary, rest in peace, period. It's clearly decreasing. As the n gets larger, the fraction gets smaller, and it should be pretty obvious that it approaches 0. So the 3 criteria for the alternating series test, sometimes they're so obvious that there's nothing to do except mention them. Did I make that clear? If you're going to use the alternating series test, you have to first show me that the problem satisfies the 3 criteria. But without the alternator, the term is positive, decreasing, and approaching 0. And so instantly, we get that the series converges by the alternating series test. Not a whole lot to do, was there? Converges by AST, alternating series test. Which is kind of surprising because a harmonic series diverges, meaning that if we change all the minuses to plus, we get divergence. And here's another something that might blow your mind. We take only the positive numbers, they form a positive harmonic series because their reciprocals are 1, 3, 5, which is an arithmetic series. So the positive terms by themselves diverge to positive infinity. The negative terms, if we ignore the negatives for a second, is also a harmonic series because its reciprocals are 2, 4, 6. It's an arithmetic series with a common difference of 2. So as a harmonic series, it diverges, but as a negative harmonic series, it diverges to negative infinity. So here's a very bizarre thing from a theoretical perspective. The positive fractions go to positive infinity. The negative fractions go to negative infinity. So individually, the 2 series diverge. But when they're fused together as an alternating harmonic series, that converges. Converge to? Well, I'm pretty sure, and I hadn't done the problem to make sure that my recollection is correct, I think it converges to pi over 4. By the end of this chapter, we'll have the tools for answering that, because I'm pretty sure, no, that's not it. I'm thinking something else. Anyway, it converges. We just don't know what it converges to. But now I'm curious, and I hate doing this on a live video, but find out real quick. A series, what does the alternating harmonic series converge to?
Okay, I found this on the web. Alternating harmonic series converge to. Check it.
Yeah, blah, 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 blah. Yeah, I know. Yeah, I just wanted to remind myself what it converged to. Are you going to tell me or not? Oh, you told me it converges. That's so nice. I already knew that. All right. But if you're curious, see if you can find what the alternating harmonic series converges to. I know it converges to something. I just don't remember off the top of my head. I'll stop worrying about it right now. Next example. The sum n equals 1 to infinity of -1 to the nth power, 3n over 4n plus 1. Now this is clearly an alternating series because it's got an alternator, and remember, the other part has to be positive without the alternator, which it is. In fact, the part that I just highlighted, so we'll go back to highlighting it, is our Bn. 3n over 4n plus 1. Let's see if this satisfies all the criteria. This is clearly positive because n is positive, so both sides of the fraction are positive. Is it decreasing? We may have to take a derivative to check that out. And does it approach 0? Remember, all 3 of these have to be satisfied in order for the alternating series test to say, therefore, the series converges. But if even one of them is violated, it's over. And one of them is. Now, we could set up a function, continuous function, 3x over 4x plus 1. Take its derivative, see if it comes out positive or negative. Believe it comes out negative. Pretty sure it's decreasing, but the limit is even easier to look at because it's a limit of a ratio of polynomials, and there are ways to find that limit really easy. Let me make that 4 look better. 4. We could use L'Hopital's rule. Both sides go to infinity, take the derivatives, or observe that the degrees are the same, and so the limit is the ratio of the coefficients, but leading coefficients. But regardless, the limit is 3/4, and more importantly, not 0. So what does this mean? Does this mean we can say diverge? Well, no. Really, all this says is that the alternating series test is inconclusive. The alternating series test only says what you can conclude when all three things happen. It doesn't say what you conclude when one or more of those things does not happen. So be careful not to read something that's up there. But does that mean we can't answer this one? No, it just means we can't answer it using the alternating series test because the third part failed. I'm pretty sure this function is decreasing. I was thinking about its derivative. Yeah, it's decreasing. But the limit doesn't approach 0, so it doesn't matter if it's decreasing or increasing. So we can't use the alternating series test. Should we use the integral test? No, integral test, everything has to be positive. Alternator prevents that from happening. Could we do a comparison or limit comparison test? Possibly, but there was one other test that we haven't seen lately, and that was the test for divergence. So remember that the test for divergence says if the limit does not approach 0, then you diverge. Well, if we were to take, let's do this. Let's write out some individual terms without adding them. In other words, let's write the sequence. If n equals 1, the alternator is negative, and we get 3 over 5. If n equals 2, the alternator is positive, and we get 6 over 9. If n equals 3, the alternator is negative, and we get 9 over 13. If n equals 4, the alternator is positive, and we get 12 over 17. And anybody can look at this pattern now and pick up on it. Signs are alternating. Numerators are going up by 3. Denominators are going up by 4. Not a coincidence because the slopes of the numerator and denominator are 3 and 4 respectively. Think about it. And what would the next one be? Going up by 3, going up by 4. Like that. All right. If we were to just look at, let's look at this from a subsequence perspective, because remember way back in the series about sequences, I threw something in there that wasn't in the book, that if you're looking at a sequence, not a sum, not a series, a sequence, if one subsequence converges to one value, but another subsequence converges to a different, then the whole sequence diverges by oscillation. Possibly infinite, but let's not go there. If we look at only the positive terms, then the limit as n approaches infinity of the positive term, so we lose the oscillator, alternator, is 3/4. But if we look at the negative terms, then we're basically doing the limit as n approaches infinity. The alternator would always be negative, and then the term is still 3n over 4n plus 1. That limit is still 3/4, but now it's negative. And so we have two subsequences in the series that converge to different non-zero values. And so the original series, the original sequence, the alternating sequence diverges by oscillation. But the test for divergence says if the limit as n approaches infinity of the nth term not equal 0, and it doesn't here, it doesn't equal anything, but it certainly doesn't equal 0. The series diverges, the sequence diverges by oscillation. But according to the test for divergence, that means that the series diverges. Diverges by the test for divergence. As you've probably already deduced by now, when you're checking a series for convergence, you have to be ready to try any of your options. In this case, alternating series test failed, but in the midst of that, we got a limit that wasn't zero, which means that the test for divergence, probably applies. And I was reluctant to say this, but I think I'm going to, because it's true. I said that if any of the parts of the alternating series test fail, then you cannot draw a conclusion. That is not entirely true. If the limit of BNs does not equal to zero, series diverges. And I'm not going to try to squeeze all the words in there, but it diverges by the test for divergence. All right, we still got a couple more to, one more to take a look at, but it won't take too terribly long. All right, so I want you to just look at this one thing for a second. Do you think this converges by the alternating series test? Meaning that we look at the term without the alternator and ask it three things. Is it always positive? Should be obvious it is. Is it always decreasing? Or eventually, not so clear. Is the limit zero? Well, the limit is zero, but let's go ahead and play this out to its conclusion. Then Q. All right, so this should clearly be positive. Because remember, our n's are positive, and when we remove the alternator, the remaining expression is positive. It does approach zero. I invite you to take the limit and verify that it does approach zero. L'Hopital's rule would be an option here. You can also multiply both sides with the reciprocal of the highest power. But is it decreasing? Remember, it just has to be eventually decreasing. If it's not evident, then look at it as a continuous function and analyze its derivative. Our function were x squared over x cubed plus 1, then what would that imply about the derivative? That would imply that the derivative is the bottom, x cubed plus 1, times the derivative of the top, so times 2x, minus the top, not that, minus the top, times the derivative of the bottom, but the derivative of the bottom is 3x squared over the bottom squared. And let's see, so the denominator is x cubed plus 1 squared. So that's always positive. And in the numerator, let's see what we get. If we distribute here, we'll get 2x to the fourth plus 2x. And then we have a minus 3x to the fourth. So we get a 2x. And then we have a 2x to the fourth minus 3x to the fourth, which is minus x to the fourth. And we need to know where this thing is positive or negative. Let's take it to the next page. 2x minus x to the fourth for x cubed plus 1 squared. If we're going to figure out where this is positive or negative, we need to first figure out where it's zero. So let's factor in x out of the numerator and get 2 minus x cubed over x cubed plus 1 squared. And again, the numerator is always, the denominator is always positive, so not worried about that. But let's think about the numerator. Our x's are all positive, so let's circle the positive stuff in green. This guy is positive. Remember, we are looking at the interval 1 to infinity, or aren't we? Well, we started this one at 5. I just did that to be random. But it won't change anything I'm about to say. On 5 to infinity, the denominator is positive. In the numerator, this is positive. What about 2 minus x cubed? Well, that's equal to 0 when x is equal to the cube root of 2. It is between 1 and 2. But when I start at 5, this seems clearly negative. We have positive times negative, which is negative, so this is less than 0, therefore we're decreasing. Remember, we just found the derivative and showed that it was less than 0 on the interval of note. So we have decreasing. That says decreasing, I promise. We have approaches 0. We didn't do it, but I told you it would be. Check that out. We have positive, we have everything we need. Therefore, the series converges by the alternating series test. Alternating series test. Ignore the alternator, see if the rest is positive, decreasing, and approaching zero. And if the answer is yes, 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 then series converges.